Okay, so let's actually look at what that wave designing tool set, the ocean spectrum and evaluate, look like. So let's make a geometry node called ocean setup. Preemptively make this one green for good luck. And let's dive into that. Now, again, the waves will actually be seen at render time, but we want to preview it here in our viewport in regular geometry time. So I'm going to say, let's make a big ol' grid. I'll make it 100 by 100. I'm going to use powers of 2 for our rows and columns here for fun. So we have 1,000,000 points again, which as we saw, this because we're not going to render this. This is just to preview what we're doing. We don't need to worry about it, the whole polygon bounding box that we just talked about. So if I were to put a mountain on it to displace it now in Geometry World, it's literally moving the points right now. They're moved. They can animate as though it were an ocean maybe, but this is not a very good looking ocean. This is just a regular mountain thing. So what we want is ocean spectrum. Now ocean spectrum does not take geometry as an input. It doesn't just move the points, because again, we're going to do it at render time. What ocean spectrum does is it makes a little package almost. It makes 4 volumes, 3 of which are the important ones really for the actual oceans, the wave's shape. So we have phase, frequency, and amplitude. These are things that you might recognize from various noise things, like the mountain that we just deleted. Amplitudes, how high it is. Frequency is how often the waves occur. Phase is kind of how offset it is in time. But they really do a lot more than that. That's just what they're calling them, but that's roughly corresponds to what they do. There's also other various attributes in here that are on these volumes that further define what they look like. The point is, this is like a package, essentially, that describes a noise that we will then pass to the shader later on so that it can apply the noise itself without it being, of course, already built into the geometry itself. We're going to pass these flat shapes to the renderer. Not this one, literally, though. To actually see what this is doing, we can make an ocean evaluate and hook that up. So now the ocean evaluate will take that package, so to speak, and then now it will do the displacement for us to say, hey, this is what that package will look like. And there you go. We have an ocean. We can do lots of stuff here. We can turn it on the ocean evaluate, which again is not actually making our waves. This is what's making and defining the waves. This is just to see them. So to see them, I want to see cusp, which is the cusp means the kind of the sharp parts of this, the tops of the waves. Visualize cusp just so we can kind of see it a little bit easier. I'm also going to go to show all objects so we can have our boat in the scene for context. So there you go. Before I go through exactly what the ocean spectrum parameters do, I just want to say at an abstract level, what is going on here? How does this work? Obviously, these shapes that you're seeing are much more interesting than just a regular noise, which is kind of just blah. Ocean spectrum is building up waves from many smaller waves. So, you have big waves, you have smaller waves on it. The big waves are moving at different speeds, usually faster speeds than the smaller waves are. Some of them are going in different directions, some variable direction things going on. All that is to say is that it's building up an ocean based on many smaller waveforms. And it uses a mathematical concept called a Fourier transform. I'm absolutely not going to explain the specific math behind how a Fourier transform works. It's pretty interesting, especially if you look up fast Fourier transform online. But generally what it's doing is it's taking a complicated thing, which is, let's say, this, and it breaks it down into all of the component waveforms that would make it up. So that's really what these volumes are doing. They're storing per voxel information that says I'm a component. Add all of us together, and it gives rise to a bigger thing like this. One way to imagine it is if you had a sine wave going across, and you wanted to replicate and pass on that exact image to somebody, you could literally make a rasterized image of this sine wave, where every single pixel stores either, a white pixel where there's no sine wave, or a red pixel where there literally is a sine wave. And you could take that picture and send it to somebody. And there's a lot of wasted data in that picture. It might be 1,000 pixels by 1,000 pixels, but only like some of those pixels actually represent where the sine wave is. It's a lot of data to represent that. In this case, that would be the equivalent of storing this geometry per frame, all million points per frame, and saving that out to disk, let's say. But instead, what you could do, instead of sending that image to somebody, you could just say to somebody, you know what? This sine wave, it's just the sine of x times 2 plus 4. Let's just say that's what the sine wave is. And that's it. Now all you have to do, instead of transferring a file that's 1 million pixels to somebody, you just are transferring an instruction. You're saying, to regenerate this image, you would just need to take this equation and then regenerate the image from this small little equation. And that's about it. So with the ocean spectrum, it's not just one sine wave. It's potentially thousands of sine waves. But they all add on top of each other to create this. So the fast Fourier transform is a way of representing that. Now, I told you all that, and you'll never actually need to know any of that, but it's nice to know that that's what's going on here, and I think it's super interesting. And this was pioneered way back in the day. I think maybe even on the Titanic movie, the oceans in that used this fast Fourier transform stuff. I think it was maybe Jerry Tessendorf at Rhythm and Hughes. Could be wrong about that, but I don't think I am. In any case, moving on, let's actually talk about the ocean spectrum now and what these parameters do.